Okay, so we've put our spreadsheet now inside of JASP to do a couple different analyses. And I think the first thing I would want to do is a series of paired t-tests. Now, we're interested in the differences between performance on the stable and volatile periods, and this is a repeated measures analysis. So a paired t-test seems like the best option to use here. To do this, quite simply, you take two items and you click go. And we can see that's been moved across here. We can add in our normality checks, see whether we should be using student's test or whether we should be using the non-parametric Wilcoxon test. And we can also add in this descriptives and plots and effect sizes. So all that information is there. Now that all that information is there, we could start moving more things across. For example, we can compare accuracy, we can compare learning rate, we could even compare points in each of these trials. Now, if we look at the p-values here, what we can see is that only one condition shows a significant difference, and that's here in accuracy. We can see that people were more accurate in a stable period compared to a volatile period, which intuitively makes sense. People would, in the stable period, they will have a better idea of the underlying probability of the environment, but in the volatile condition, it keeps changing, so they have to keep relearning. So it's less clear what the high value options actually are. However, we hypothesized that learning rate would be significantly higher in a volatile compared to a stable condition. Unfortunately, that does not seem to be true here. I think, like I say, I would have liked to spend more time with this. I think I've calculated learning rate using an off-the-shelf tool, which has done a reasonable job, I believe, but I know that if you go to the Oxford Comp Neuro GitHub, and I put a link to this on our webpage, then you can actually download data from this experiment, which they use to teach computational modeling, and they also have MATLAB files that you can download, and you can run the exact analysis run by Behrens and Browning in MATLAB. And I think there are versions of their analysis that take into account risk aversion. Are people risk-seeking, so they're more likely to take a gamble? Or are people risk-aversive? And you can take that into account when you're calculating the learning rate. And that's something I haven't been able to do with my off-the-shelf learning rate. I think that would have a big effect. But for the time being, we can't support that hypothesis. We do not find, although we see a small increase on average in learning rate in the volatile blocks, we don't see that as a significant effect. Looking down here at the normality checks, I can see that actually learning rate is not normally distributed. I can turn on the Wilcoxon analysis, but we can see that it has very little difference in this case. The effect is just not there. So yes, when you have a p-value less than 0.05, it means the assumption of normality has not been met, and that means you need to change your test. So in this case, we use students paired t-test, except here we would use the Wilcoxon test. In terms of reporting these results, you would always report the mean and the standard deviation. In the case of the Wilcoxon test, because it's non-parametric, you would report the median rather than the standard deviation. So in a sentence, which we're going to type up here, you'll say something along the lines of, in stable condition, accuracy was mean 68% with a standard deviation of 1%, compared to 63% with a standard deviation of 0.99%. And then the t-value we're going to put in to support the significant difference can be seen here. So we have t, brackets, degrees of freedom, equals the t statistic, and then we have smaller than 0.01. In the case of the Wilcoxon test, you'll need to calculate the median, and that's not here in the current descriptives. You'll just need to click on descriptives in the top left, and you'll be able to get the median through the drop-down menu statistics and ticking the box that says median. Then you can replace the mean with median, and you can put W equals your Wilcoxon statistic, comma, p-value. So we're going to continue now with the learning rate, because I had hypotheses about learning rate. Also, I'm going to continue with the accuracy measurements. And the next thing we talked about was the order effect. Maybe this learning effect is not there because there is an order effect, and whether people started with stable or if they started with volatile, maybe that has an effect. So to do this, we're going to go to a repeated measures ANOVA, and I'm going to say the environment, which is stable or volatile, and under order, I'm going to move that as a between subjects factor. And what that means is that there's we want to account for that difference between our participants. Our repeated measures cells, however, are the stable accuracy and the volatile accuracy. And we can see under here, it's run the calculations, and it told us that there is a main effective environment. So let's actually pull up a plot, because I think it always looks better in a plot. I'm going to make the order separate lines, and I'm going to make the environment the horizontal axis, and I'm going to add some error bars to this as well. And here we go. So this illustrates the data perfectly. There is still an effect where people are more accurate in stable than volatile environments, but you can see that whether they did stable first or volatile first has no effect. And we have no environment by order interaction. We also do not have an effect of the environment, an effect of the order. And in order to put this in an ANOVA, we're going to write down the following formula, which includes F, the degrees of freedom, the residuals, which go inside the brackets. We would then include our F statistic and a p-value. If you wanted, we could also include some effect sizes. For example, something like partial eta squared. That could be used as well in your report. I'm going to now just put on, because we had hypotheses about learning rate, I'm just going to change the analysis. So let's put in learning rate stable and learning rate volatile. Now we can see here that none of these effects are significant. We can see a bit of a crossover. It's not enough for a significant interaction, but it does seem like participants have higher learning rates for whichever task they did first. This could mean that maybe participants were experiencing fatigue, and they were fine in whatever block they did in the first part, but they then got tired for the second half. That's possible. Maybe they needed a break in between the trials, although I believe it took on average about 12, maybe 13 minutes, so I don't think that's likely to be an effect, but we would report this null effect in the same way. The ANOVA would include the degrees of freedom, comma, the residuals, the F statistic, and the p-value. And in this case, we can say that there is no effect of environment, order, or an order by environment interaction looking at the learning rate values. So one thing we mentioned as well, I'm going to pull up now a correlation analysis, and we thought that there might be a relationship between learning rate and points scored. So people who get more points are the people who are more adaptable. So we can look again. I can take my two learning rate parameters, and I can then, at this point, take my points score. I'm going to tick to flag significant correlations. I'm going to display it pairwise because I think it's easier to look at. And I'm going to get scatter plots so we can look at the data and we can see where there's a correlation. We can see that here there is one significant, hugely significant effect, and that's related to points scored. People who got more points in the stable round got more points in the volatile round. Basically, people who are better at the task. We should also do our assumption checks at this point, and what we can see is that there are a few of these elements where we can see that basically normality is not met as an assumption. So it could be worth including Kendall's tau in this. And Kendall's tau is essentially a non-parametric correlation. What we can see now, actually, as we've included Kendall's tau, we can see why it's worthwhile doing these normality checks. Because we had something here that was on the edge of significance, so a p-value of 0.05, and that's the relationship between volatility and the points scored in the volatile round. That effect in a non-parametric, once we do a non-parametric test, because the data it does not meet the parametric assumptions, we can see that we have a significant result. And we can see, this is the plot that's relevant here. People with a higher volatile learning rate scored more points. And that's a very logical result. Interestingly, though, we don't see that in the stable comparison. There doesn't seem to be a relationship between points scored and learning rate in the stable block, but there does seem to be that relationship in the volatile block, suggesting that participants who have a higher learning rate scored more points. Interestingly, actually, it's not significant, so we shouldn't read too much into it, but there does seem to be a negative trend. So people with a lower learning rate in the stable condition scored more points, which matches what we've spoken about learning in stable and volatile conditions. So this does provide some support to this idea that you want high learning rates in volatile periods, but low learning rates in stable periods. And we can see that based on the amount of points people accrued. But only this is significant, and we would report that by including the R value and the P value at this point. The last thing I'm going to do now is look at our comparison with anxiety. Is there a relationship between learning rate and anxiety? In order to do that, I need to create a new column, because in the papers we wanted to look at the difference. So I'm going to say LR V minus S. So this is learning rate. Let's drag that down. So we have learning rate volatile minus learning rate stable. So I've just hit compute and it's created that column for me. And what I'm now going to do is I'm going to get a new correlation analysis, and it's going to be learning rate VS, and we're going to take our neuropsychology scores. You could also, if you want, do this as a regression analysis. Let's report again pairwise, flag significance, and I want my normality checks. So we can see again that in a lot of these cases normality is not met. So I'm going to throw on Kendall's tau as a non-parametric version. Now, one thing we can actually see, No. Let me put on the scatter plots. While scatter plots are being generated, we can see here there is a significant result. And in fact, there seems to be a relationship between anxiety and learning rate. And what it looks like here, interestingly enough, is that as people's somatic anxiety increases, so these are people who are more aware, they feel their heart beating more, they feel the pulse in their face, they have those physical anxiety feelings, those individuals are showing more of a difference in their learning rates. In this case, a positive value refers to the fact that people are increasing their learning rate more in the volatile than the stable condition. So actually what we see here is the opposite of what Browning saw. Browning saw that as people's anxiety increased, the difference between volatile and stable learning rates decreased. So it's a negative correlation. Whereas this is a positive correlation, saying that people who have more physical anxiety, they are showing a greater difference between volatile and stable learning rates. So it's difficult to know how to interpret this, and I think perhaps before we even get into interpreting it, we can see here that this shows the opposite of what we just saw in the previous correlation. Here we have a significant result using a parametric approach, but that's not appropriate because very clearly the normality, the parametric assumptions have not been met. So using a non-parametric Kendall's approach, it's no longer significant. So this shows you why it's worth having a look at these different assumption checks to make sure that you use the correct correlation analysis, whether that's Pearson's for a parametric analysis, or whether Spearman's for rank, or Kendall's for the full non-parametric approach. So, and there we go. So our hypotheses were about differences in performance in stable and volatile blocks. And yes, we saw that there was clearly a difference in accuracy, telling us that our participants were able to do the task. We didn't see the learning rate effects that Behrens and Browning showed. And I think this has to do with the way I calculated learning rate. Or it's possible that we just didn't replicate that finding. What we do see, however, is that there was a relationship between learning rate and points scored in the volatile blocks. So people who had a higher learning rate in the volatile period scored more points. And that does go some way to supporting this idea that we want to upregulate our learning rate in a volatile period. We want to be adaptable to get the best out of a volatile world, whereas we want to be stable and we want to have a low learning rate when the environment is not changing. In terms of our relationship with anxiety, we did see a trend towards one result, but we can see that by correctly dealing with the normality checks, that didn't hold up. And that makes sense because it was a bit of an unusual result. It seemed to fly in the face of what Browning had shown in the past. However, this, again, like everything, replication is key. So if you guys want to take on this experiment and you want to run it at your universities, and we would love to know, we'd love to have the data added to our data sets, and we'd love to know if we can replicate these findings when you guys do it as well.